Okay, we're going to get into integrating using partial fractions, but before we do this, we're just going to define a quick result, which is going to help us with this, and that is that the integral of a quotient between the derivative and the original function is equal to ln mod f of x plus c, and this is because of the way ln x or ln any function of x differentiates, okay, using the chain rule, because ln x goes to 1 over f of x multiplied by f dash of x, okay. So yeah, that's the first thing. Then we're going to now look at an example of how this applies to partial fractions. So if we want to integrate a function in this form, so bear in mind all the constant terms could be completely different, but it will look like this, okay. So we'll only have a maximum power of x on the top, but it could just be a constant, and then we'll just have a quadratic on the bottom, okay. That's when the method I'm about to show you applies. If you get other types of partial fractions, you're going to have to do a different type of partial fraction decomposition, but in this case this method works. So we set 2x x plus 1 over x plus 2, and we try and decompose this into the form a over x minus 1 plus 1, sorry, plus b over x minus 2. And so to do this, we need to find a and b such that this is satisfied, such that this is true. So 2x is equal, well, is identical to a x minus 2 plus b x plus 1. Now there's two ways we can do this. We can either substitute in values of x or compare coefficients. We'll do both here. So just skip this if you know how to do it, but otherwise check it out. So if we set x is equal to 2, substituting that in, because bear in mind this triple identity means this is true for all x values, so we can just substitute in random values of x, but we're not substituting random ones, we're choosing x so that either a or b disappears, so we can have an equation in just a or b. So this gives 4 is equal to 3b, and that implies b is equal to 4/3, and then we can take x is equal to minus 1, and that implies minus 2 is equal to minus 3a, and that implies a is equal to 2/3. Okay, the other way is by comparing coefficients. So that just means that the x coefficient has to be on both sides has to be the same, and the constant coefficient on both sides has to be the same. You can apply that method to lots of different areas of maths. So I'd encourage you to try this because it's useful everywhere. Okay. So the x coefficient on the left hand side is 2, and the x coefficient on the right hand side is a plus b. Okay, because we have an ax minus 2a, but that's got no x dependence, plus bx plus b. So the only terms with x there are ax and bx, so the coefficients are a and b. Okay, so hopefully you can see that. And then the constant coefficient on the left hand side is 0, and the constant coefficients on the right are b minus 2a. So this implies b is equal to 2a. Substituting that into the first one gives 2 is equal to 3a. Look at that, gives us exactly the same value of a as before, and if b is equal to 2a, this gives b is equal to 4/3. Okay, so those are the two methods. Obviously we get the same answers. So that means this integral is now the same as the integral of 2 over 3 x plus 1 plus 4 over 3 x minus 2 with respect to x. And if you can see, this function on the bottom, just this bit and this bit differentiate to 1, okay? And all we have in both of these are scalar multiples of 1. Alright, so we can write this integral as 2/3 1 over x plus 1 dx plus 4/3 1 over x minus 2 dx, and that, integrating that using this rule at the top here, gives us 2/3 ln mod x plus 1 plus 4/3 ln mod x minus 2, and then plus a constant integration. So hopefully you understood this method. It will be quite useful for a lot of integrals. So yeah, if you're not familiar with partial fractions, be sure to practice that. I've got a video on that I'll link. But that is it for this video. We're almost done with integration. I think what we've got left to do is some separable differential equations, and then we'll be moving on to the next topic. So thank you very much for watching, and I hope to see you